How long is this for, Krupa? I didn't even look at the length of time.
So you get 55 minutes for your talk, but we'll give you like a 5-minute-ish warning if you want to hold a time for answering questions and things like that at the end.
Yeah. Well, actually, I like people to, throw out questions during. It's okay with me,
Okay. Yeah. I mean,
even if they want to unmute, it's okay with me. I like the in-person experience, but
yeah.
which is it's usually a boisterous crowd in person. You get 20 people talking at once.
Oh boy.
I'm not sure that's easy to manage either.
Yeah.
It's more fun, but hold my weight on here. Let's see. When do you want to start? A few more minutes, or?
I think we're officially slated to start at 2:35.
Okay. All right. Set my phone next to me. I feel like though the sitting a lot, I have to do exercises. My leg falls asleep if I sit in front of Zoom all day.
Oh yeah, for sure.
We should have a moment of calisthenics, Krupa.
That would be exciting. If we had a talk in the middle of the day where we made everyone do Zumba, that would be fun.
There you go. You could lead that, right?
Oh God, no.
Oh, come on.
No, I would be terrible at it.
Yeah, I wouldn't even try at my age. You kidding? I'd probably die.
No.
We would have to do a pattern, a test pattern. Here's Joe's speech. He died.
Oh my goodness.
I don't know, Lou. You appreciate that sense of humor. I don't mean to pick on you. Lou's at the controls right now. Well, my cats are leaving me alone today, which is good. I usually like to run the computer.
For some reason, that's something my daughter's cat does to her, but not me. It doesn't run my computer.
You probably swatted it. You probably swatted it a few times.
No, I didn't, but I probably took her off the keyboard more than once. But she's got a reason. I'm not sure what it is.
How you doing, Joe?
I think they like the warmth of the, you know, they lay on the keyboard. It's a warm area to hang out
That could be. And it's got whatever sweat your fingertips have left on it.
Yeah, that's true. That's if the cat likes you, Bill.
Exactly, which it may be the situation. Maybe it doesn't like me.
Yeah, my problem is I got cats following me around outside, inside, day and night. I switched to their standard awful cat food. I threw it out the window, and then I thought when the prices kept going on cat food, I said I'm going to switch to real tuna fish.
Uh-oh.
Well, my wife said, "What are you giving? Yeah, that's not healthy for cats." So I wait till they go on sale. White tuna fish for in water for 88 cents a can.
Well, you don't want to hurt the cat.
You should see their coat after 3 months. You should see the cat's coat. Coat. It's unbelievable.
Good.
They all look like they're show cats after eating tuna fish day and night.
Okay. Well, good then.
Yeah.
So we're going to get started here with our next talk, which is going to be ultra low energy structural health monitoring sensor platform by our very own Joe Jessen. So Joe is the CEO of RF Sigint, which is a wireless sensor patent advisor company, and he's the CTO of AGILE Devices and AssureNet. He has 25 plus years of experience in designing and implementing, and he works with telematics, M2M, IoT wireless sensors, embedded systems, and he was awarded GE's Top Innovation Prize, the Edison Award in 2008. He has been awarded over 15 patents and has worked on the original Tempest Signals intelligence program in the 70s. He's also an adjunct faculty member here at the TCNJ Electrical and Computer Engineering Department since 2013. He's also the IEEE Princeton Chair and holds graduate degrees from DePaul University in Chicago and is currently a doctorate candidate at NJCU. So without further ado, let's give us warm virtual welcome to Joe Jessen.
Well, thanks everybody. I think you'll find this very interesting, and I'll tell you a little bit about where I came to this. I've been doing a lot of sensor design, and don't let the 25 years fool you. Kat said he will not put my real number of years experience on it. It looks bad. Too many years. But he basically, so I've been working with wireless sensors for a number of years, and the college in New Jersey received a grant about a year, I'm going to say it's a couple of years now, two years ago, on to investigate the use of wireless sensors that would be embedded in concrete and in wooden structures and be able to be tracked anywhere. The company of interest is Tenna, and the parent company is a construction company. So they're a worldwide construction company, and they have to find everything. You know, they have to find things. So we came up with this idea of let's being able to track large construction items. And so the college got a nice grant, and so I teamed up with our own Dr. Brennan, and we worked on different sub-projects on this, and we also delivered the grant, which was being able to track Jersey barriers, large concrete structures. It's not they're so expensive, but when you need them on site. You have to know where they are, and it's a problem. So what we did is worked on the technology needed to find large concrete structures on construction sites. And so that was kind of an interesting problem. So it ends up leading me to this idea of a significant area of research, which is understanding the bridge health or structural health monitoring is very important to me. So I did a lot of research on that, and we kind of joined forces on the grant. We had to understand how RF performed in concrete, and we had to understand how to do very, very low cost sensors that again would work into structures like concrete, which is, it isn't the easiest thing in the world. But you know, the allied problem in another discipline is this whole idea of bridge monitoring. So I'm going to start off by talking about this bridge case of I-35 that basically collapsed August 1st, 2007. So the immediate reaction was, how come no one was monitoring this? And you know, typically what the federal guidelines are is there has to be visual monitoring. And the Federal Bureau of Transportation lists 70,000 bridges that are structurally deficient, and more than 77,000. Now that number is a little old. That's I think comes from 2010, but it's much worse now. The problem with bridges is if you look at the life of the bridge, many, I don't know if most, but many of the bridges in New Jersey, for example, are beyond their rated life. So the federal guidelines is that the structure has to be visually inspected once a year. So you have a lot of consultants and professors running around looking at cracks in bridges. And even if it's not structurally deficient, the others have to be inspected once every 2 to 5 years. And again, a lot of bridges, if they're built turn of the century or they're 75 or 100 years old, what happens is you don't have enough money in the budget of the state of New Jersey to replace the bridges. So, but you have to be on top of it to avoid something like this Minnesota I-35 collapse, where people died in this particular one. And what I was going to say is their next reaction was to build a new bridge, but then put sensors to understand the health of the structure. So I want to just give you a glimpse of their response to this thing. So the St. Anthony Falls Bridge was a replacement for the I-35 bridge in Minnesota. And but I wanted you to look at the actual technical paper they did, where they ended up putting sensors in these locations shown on the bridge structure. And if they start looking like a big number, you have to actually look at their summary of static instrumentation and sensors that they're using for that. So if you look to the right, the replacement bridge, they ended up using 135 vibrating wire strain gauges and 9 of a certain type, or 139 of one model, and another sensor of SM5 of 9 of those, 139 and then 9, and then a different manufacturer, broken vibrating wire strain gauges. So they're very interested in monitoring strain at multiple points. So when you start adding the number of sensors, they're looking at just the strain gauge. It's incredible, you know, it's well over 200. And then they had resistive strain gauges, which are analog differential type of strain gauge. Fiber optic strain gauges. So they had a deformation sensor of 12 of those, 24 of the resistive. And to measure temperature, the resistors, they put 48 sensors of temperature, 12 linear potentiometers. And basically, you know, I started looking through this, and the theme of this, my entire talk, is how do we get the energy reduced on a sensor platform? And that was my area of research, and that's the one we did practically with funding from TENA. So in this particular case, this is kind of a worst case example because it looked like they just added sensors just to be cautious. They go from, you know, no sensors to almost 500 sensors, and they're connecting them directly versus copper and optical termination into a logic box. These are 19-inch racks of equipment, and I was able to calculate over 200 watts of power consumption just monitoring the bridge. So this isn't a good end state. I'm sure the installation was well into the 7 figures to install all these and to manage it. Let's see here. Okay, so let me jump into this slide. Talks about the 3rd generation. Now there was a 2nd generation between 2007 and a 3rd generation, which is the use of, and I'll go into this a little bit more. So it was where they decided to go wireless instead of run all the copper directly and optical, but to look at a fiber solution. And this slide talks a little bit about and this is state of the art. This is from 2021 and 2022. In fact, it was a 2022 publication that just we're going to get into that was done from the University of Trento. And what they were doing, and what was cool about the whole design, which I'll get into, was it was designed stage by stage to be the most energy efficient. So if you have a goal of reduced energy at each stage of you start solving the biggest weakness in all these designs, which of course is power supply. You don't want to have you don't want to be in the situation replacing batteries on bridges every few years or every year or every 6 months. I mean, that's ridiculous. You can't do that. It's effectively not a viable approach, and it becomes very expensive to do that. So really, if you focus on the constraint, engineering is all about constraints. What do I have to work with? Where can I go? So if you focus on energy, you realize you cannot even be connected wirelessly. So you have to make decisions remotely, right on the processor, right on the remote unit. So what in this example, here's an example of state-of-the-art structural health monitoring, is you have sensors, and most of these sensors, which are really interesting, what you're seeing in 4.0 or 4.0 is the feature extraction, and what you're seeing is a damped oscillation. So, and the data collection itself is converted is from an accelerometers. It's obviously accelerometers that they're using in this paper, and they're scattered accelerometers, and they're making decisions on the data coming off the accelerometers. So there's a Fourier power spectrum that's derived, but each structural excitation, it could happen when a known truck comes over or a train comes over the bridge. There's a predictable excitation of looking at the bridge's FFT, or frequency spectrum coming in from it, and it's a pattern. So there's a fingerprint you have. Now where that comes in is then the neural net is trained on the expert identifies the waveform in 4, and in 5 they train to identify the supervised neural network on learning the pattern. And then the output of that becomes an event or a trigger selection. And then that trigger selection is then sent wirelessly back to a portal in a data collection. And usually it's low traffic, and I'll get into that, but it's pretty cool. So this is really the whole platform and methodology, the design of this thing. It's to keep it simple. Now, when you look at when you go from a wire strain gauge to a MEMS type of accelerometer, you're talking an order of magnitude of money. One is One is in the area of under $5, which is the MEMS, and you could go into $200, $300 per sensor on the other vibrating wire side. So, and again, if I can get by with a MEMS accelerometer, I really want to go in that direction. Why? MEMS accelerometers are produced well over 1 million a month by one company alone, produces 1 million. And where they go into is automobiles. They go into airbags. So the Analog Devices makes a boatload of these sensors, and they're very, very nice, very predictable outcome. They calibrate it for results, and then they put a learning system around it in your automobile, because they don't want the airbags to go off at just because you hit a pothole. So they want to know the pattern coming off of the airbag. So again, you have a neural net, artificial neural net, or some variation of a learning network that then triggers based upon a trained algorithm that's programmed, or a net that's programmed into the airbag sensor. So again, if you start making 1 million a month of these things, you can get down into they're probably paying under $1 right now for it. But last time I looked, it was slightly under $5 for a very, very precise sensor. And again, it has to go off. It kills people if it goes off. The person sitting in the seat that's underweight and an airbag goes off, you want to make sure it didn't go off on a dumb pothole. So there's some intelligence and machine learning that has to go on. So you trigger based on it. Okay, so that's the state of the art, what I would call the 3rd generation. Now, what's interesting about the architecture, I sat down and I said, well, what's the architecture you'd want on an ideal structural health sensor? Well, you know, every sensor, you have sensor inputs, sensor 1, 2, and N, and application, that's your microprocessor or your embedded microcomputer. And then you have the machine learning event classifier. And again, that's the latest twist on a lot of these. And then you have a communication element. And then you have a power supply, which could be battery. Right now, you can, in the right type of design, in other words, if I minimize energy required by the sensors, the application, the NPU, and the communications element, I'm really making some major progress. So if you look at my note above, so the power in the I misspelled that, that's the wireless sensor network, in 2nd generation is much, much higher than everything else combined. So my attention that was spent in the last 2 years is focusing on this wireless sensor network power consumption of the, which I call the communications element. So the other part of the puzzle that a lot of people don't understand or conclude is if I'm taking energy out of each one of these elements, or I'm going to take the largest amount of energy consumed, which is the communications element, and I can reduce that greater than 10-fold. I also have to look at the energy going from each of these elements, or being consumed by each of these elements. I'm also going to understand where the RF energy is going. And it's a very important concept, because the actual gateway or base station that you're going to use to collect your data, you have to understand the trade-offs and what type of protocol is ideal for what we're doing. And again, I was working inside of concrete, where I'm actually transmitting inside of concrete. And but if you do this path correctly, and let me see, I got an example here. So this is one, the path without concrete, and this is after I embedded it in concrete. and this is an example of what actually I'm looking at here. So if my legal limits on a, and let me use as an example, LoRa is one of the categories of a new set of chips called long range modules. So these are long range protocol modules that support a certain, that are also optimized for energy. And I'll show you how they do that. Let me see real fast here. Okay, so let me jump ahead and I'll come back to where I was. So basically, Shannon-Hartley came up with this relationship. Now it's not indicative. You can't solve a problem with just looking at this equation, but it gives you a general framework or direction of where these new chips are coming from. So what this says is that, you know, in an era where everybody was trying to optimize channel capacity in bits per second, it's a function of channel bandwidth and noise and signal to noise ratio, SNR, as a linear power ratio. So you flip the equation over and say, look, I want to solve for improved, I can get by with worse signal to noise if I can lower my channel capacity. I can lower my bandwidth and improve my signal to noise. And if I work on that, I can not only get greater distance, you know, at the expense. Here's the expense. In engineering, the trade-offs are always there. So I can't send video on any of these LPWAN chips. Can't send video. I can't even send fast text. I could send fast text, but it's basically at a very low channel capacity, and I control the bandwidth. I make it narrower and narrower. I program it as narrow as I can. So a lot of the chips are known as, of the LPWAN umbrella, they're also known as the very narrow bandwidth or narrow band. Some of the chips themselves in the cellular world, we're going to get into that, but that's pretty cool because they actually have defined in 5G a whole class. We don't think of 5G as very slow, right? But there's good reason to have very slow bandwidth on utilize certain of the LTE blocks in 5G. But okay, so I just wanted to show you the framework that Claude Shannon had set up years ago, and everybody's been chasing C, and I'm just now all of a sudden people realize what you need for sensor, especially smart sensors. I want long distance and I want very low power. Okay, so that's where these come from. So there's two types of LPWAN supported PAR chips and modules. LoRa is the link layer, and that stands for long range, and that's an actual name of and if you can order these from Semtech. They sell the hardware and the chips itself. They're controlling their IP, so they're getting their license on their. And this is an optimized protocol. It isn't just a narrower bandwidth, but they do some other features. So they use the code, spread spectrum code improvements, and they use other types of forward error correction. And they look at fade and propagation. Propagation is a big can of worms. So anyhow, these are specific protocols people come up with, and LoRa is one. Now LoRa by itself is the link layer, and LoRaWAN is set up so it's routable. So you have a network layer built into the chip. Sigfox was the first generation of ultra narrow band. So this company pioneered very narrow band chips that would get up to 20 kilometers line of sight and consume power that would last on a coin cell that would last for over a year with one simple little coin cell. And TI has their own, they call it just generic sub-gigahertz. So what does that mean? Sub-gigahertz means that for greatest propagation distance, you have to work below 1 gigahertz. and it's narrowband, as we mentioned, to meet the Shannon model. That's the license free. So anyone can get on, can have a LoRa chip and transmit, because it uses the spectrum called it's the scientific medical protocol that's free. It's the same one that's used for RFID. There's no fee for that spectrum. Now there's license band. The 3GPP was a standards group to work on the same problem. How do we get much greater distance, much lower power, and we're talking 10x improvements at least, and much lower power, much greater distance in the cellular world. So that's narrowband IoT, NB-IoT. That's the actual name of it's very popular right now in Asia and China. I would say 90% of all sensor platforms that are being installed in China on bridges, dams, and I see a lot of papers come through, peer-reviewed papers out of you know, Elsevier. Okay, LTE-M is the long-term evolution, which is a little bit, with NB-IoT, you get what's called a 20 dB margin improvements. That means you more than double the distance, and the power is less than half what you would get. For every 3 dB, you reduce the power in half. And that would be on the attenuation side. Boost side, you can add 3D, you double your RF power. LTE-M, so that's the evolution. They call this the long-term evolution narrowband, and both of these are included in as a standards committee, 3GPP standards group committee that sets cellular standards and is part of the 5G. Okay, so let me go back here. So in this example here, I've got a 20 dB transmit power coming, and this is a LoRa example. So I can buy a LoRa single chip that's got a processor on it. I can do some applications work on it. I can do some, I can transmit, I can develop the protocol, send data to it. And I have some that's set up to do anything you want. It basically, the legal limits is 20 dBm. So that's definition. It's in decibel, which is a ratio, and reference to meter. And so this is plus 20 dB transmit power. Now you have a little bit of loss. I have 1 dB loss on the cable and 2 dB I gain off the antenna. Now the I means it's a ratio relative to isometric antenna. And then you see free space path loss. So this tells me if there's nothing in the way, and there's no trees, there's no any kind of metal, anything to affect the attenuation. Now it's 700 to 900. These are at 930 megahertz with LoRa. That's the legal space bandwidth, or the legal spectrum that you can use is 900 to 930 megahertz. Anyhow, so what you get is minus 147.32 decibel of attenuation. It's minus, so it's being attenuated in free space. And so I lose obviously the most through just propagation through free space. And there's nothing in the way. This is done. This is the example is a satellite. So in order for me to transmit to a LEO, low Earth orbiting satellite that's 600 kilometers in orbit away from me, I'm losing, just in the space of transmitting, I'm losing a minus 147.32. So this is, I'm sure, one of Dr. Katz's problems in his classes. I think he does the moon, but this is going to a LEO satellite, 600 kilometers. So what are we doing this? So we're really doing accounting. This is a link margin. So when we get to the receiver antenna, you get a little bit of boost, 2 dBi. So you got an antenna with a 2 dB over isotropic gain antenna. You got a cable, you're losing a little bit on the cable, minus 1 dB. And then you're going into a LoRa gateway, which is receive. There's a certain type of power you need to be received, right? So this is the sensitivity side of the receiver on a LoRa receiver. So if you look below, you'll see that the receive sensitivity is minus 137 dB reference to an M. So minus 137 dBm is 11.68 dB lower than the signal that we calculate you're going to get. So we calculated, when you start adding, summing up the positives and negatives, the losses and the gains, you get to minus 125.32. Well, the difference between that and minus 137, which is the chip's sensitivity, is 11.68. That's your link margin. So that says that you have, less negative is obviously a good thing. I mean, then you're in the positive direction by 11.68 dB. That's your margin. Now, if I go ahead and drop a concrete slab over the antenna, I'm not going to have free space propagation loss. I'm going to have additional losses, like I calculated. So in this particular case, I can reach with an end user device with 20 dBm transmit power. That's to a milliwatt, by the way. The M is for milliwatt. So that's your reference. And so I'm transmitting 20. By the time I get to 600 kilometers in space, I'm going to communicate to the LoRa gateway off the satellite. I've got plenty gig link margin. It's going to work well. As long as, like I say, I don't have anything obstructing the path where the minus 147.32 is more negative, then I won't hit. If it's more negative by another minus 11, I won't have anything left on the link margin. I'm going to run out of link margin. Okay, so I think that's a good example of what network engineers. Now, this isn't just with LoRa. So people that are designing 5G. I was at a 5G workshop on how to design, how to implement 5G systems, and they have a whole computer-aided simulation tool that you plug in these numbers on the gains and losses, and it comes up with the link margin to your 5G, which is really multiple blocks of LTE blocks. Okay. All right, so let's just go into 5G since we talked about that a little bit. 5G is really a triangle of sorts. I mean, you could look at it as a triangle, but most people, when I say 5G, they think of fast video, which is true. When you look at enhanced mobile broadband, so that's your bottom side called EMBB, and that's 5G lingo for acronym for enhanced mobile broadband. But look under that. So that's going to give you gigabit rates of speed, which I've never tested 5G other than what I get from T-Mobile, which is not really that enhanced in this area. I don't think I'm getting a gigabit rate. They're still throttling it back, although they say they're not. But so okay, so 5G. If you're, again, here's the problem: you got to deal with the Shannon law. The Shannon's law says you have to be close. It doesn't work over great distances. You got to be really close to your 5G base station for you to get the full bandwidth, multi-gigabits. Now, let's suppose you want to use a sensor platform. Well, you don't care about that. I'm not doing multi-gigabit. In fact, I'm doing less than I did a few years ago because I have a machine learning classification and trigger system in series. So then it turns it into a few bits. No big deal, right? So I don't want speed. I want distance. And hey, if I can get 20 kilometers, hey, I'm very happy. 15 kilometers. In cities, it can go down to as low as 1 kilometer in our testing. And I think the 1 kilometer was with with inside of concrete. So you had to allow roughly 15 to 20 dB attenuation if it's sitting in concrete. But by the way, this, let me go up to the other. Okay, so deep coverage, if you look all the way the other extreme of this triangle, and it says deep coverage to reach challenging locations. Ultra low energy, 10-year plus battery life. So I read the 3GPP specs for the cellular manufacturers, and they specify it not in millijoules or milliwatts. They specified how many years can I get out of a typical lithium primary L123 battery, or some generic low lithium primary. If I can get 10 plus years, I meet my goal. So this is what we're talking about now. This is nirvana for a sensor designer. So you give me deep coverage, right, inside of the earth. You can give me inside of concrete, inside of wood. It'll work fine. And I'm dealing with 10 plus years of a lithium primary wide temperature battery. Hey, that's great. It's even better than what, so, and it's ultra low complexity. An NB-IoT chip is very low cost, and it's not as complex as even a full LTE bandwidth chip. And here's the other bonus. So now I can scale this thing because I'm not dealing with huge capacity, right? So I'm going into my base station, which is acting as the concentrator, and I can have 1 million plus nodes per kilometer squared. That's cool. They call that ultra high density. So you got to come in at the right protocol. So the right protocol is LTE-M or NB-IoT in cellular. And again, you don't, if you need gigabit rates, go to the bottom. Now there's another class of applications that need ultra low latency. They call that mission critical. So if you're doing some remote robotic surgery and you're in another country, so you need a network connection that has 1 millisecond or so of latency, because you're controlling some servo motors, or you're actually in the control loop, which scares me. When you take a wireless network and you're in the middle of a controlled surgical loop. But anyhow, that's called mission critical, or URLLC on the 5G side. But you see where we live. So we're on this massive Internet of Things. That's also known as sensor platforms. I went through this slide, license, it splits as license free versus license banned. I talked about this a little bit, and Shannon's ideal system that goes actually the noise floor, and if the protocol is set up right, you can actually work below the power noise spectrum density. Here's an example of performance of so when I select the chip to use either LoRa or LTE-M chip, I'm looking at what the receive sensitivity of that chip is, and in this case, this is a SX1276 LoRa chip, and I've taken that directly from their spec sheet. So I'll go right over to where I have a nice receive margin, link margin, and you can see what I have to do on the y-axis is bit rate. So I have to reduce the bit rate to roughly 18 bits per second. Not exactly video rate, but perfect for a sensor, you know, because I'm sending flag signals, whether it's in or out of control, or whether there's an event that occurred. And I'm actually processing the data on the part, on the not the communications part, but on the MCU. I have a low power. I'm selecting neural net stacks to be low power, and I'm basing it on the basis of one paper I just read was 55 millijoules per classification. So interesting how the design word is all going for energy per function. And so this says I have to really get down into 18 bits a second if I want that particular performance and achieve that receive power level. Now, those capabilities are in the LoRa chip. I could set the sensitivity to whatever I want by changing the data rate and the bandwidth. So it allows me to change the bandwidth. Sensitivity rate is a function of bandwidth, and it's also a function of, they use I mentioned they use spread spectrum to also improve the noise immunity. And so there's also that spec. I can control the spread. So the best the most sensitive receive power in a LoRa is the minimum, the smallest bandwidth. And I think it's 10 kilohertz. It's the smallest bandwidth. And there's a reason why you can't get that far, but with inexpensive hardware. But it's, and then I can increase the spread over that entire 10 kilohertz, and that gives me the best RX power. Okay, so this is some work I did previously on this is what I call a second generation satellite system, where we wanted to put a system together that would transmit location and motion triggered reports on assets like trailers. But it has to be self-contained in the size of a marker light. And that's pretty big, but we're talking 53 foot and 57 foot trailers here. And so anyway, I designed this product, and it's we had to do a lot of I think the 13 bits per second was where we ended up with, very low bit rate to get the signal to noise that we needed, the sensitivity we needed on the receiver. And this was second generation cellular, so we couldn't turn it on that much. So we were up to 2 events per day for 7-year battery, which is pretty cool, actually. We were the first to have a 7-year battery at 7 years. In fact, this design was purchased by another company so they could put it in production, high volume production. And gives you some idea what the first generation of or second generation of this hardware was. So this module in the middle marked Wavecom. So that's a standard GSM module. And again, all I could get out of it was 2 events a day with the primary lithium. And the lithium was not a rechargeable, like I said, it was primary, and it was built, originally it was designed for the military use. So it had great temperature, 150 degrees, no problem. Let's see what the thermal range was. It's pretty good, and it was good on the low end too. A lot of lithium rechargeable don't work on very low end, below freezing. It has problems. So this was outside, obviously, underneath a truck or a trailer, and we had to boost the sensitivity of the GPS, so we were able to use differential GPS to get improved sensitivity on the GPS market, which is the weak link in all these sensor platforms. Because once you include location, guess what? A GPS, or technically you call it GNSS now, because the new ones all combine international satellites. It's not just the Air Force managed satellites that we have in this country, but we have over in their medium Earth orbit satellites for them. GNSS. Anyhow, so these are the kind of tools that we could look at. You can't just put a resistor in series when you're trying to monitor power, because it turns out it does not respond well between, you cannot measure between microamps and amps. You just don't have the dynamic range. So this is a special piece of equipment made by AGILE to give you, if you look at the peaks on here, the peaks are 829 milliamps, 0.25, almost an amp. You're seeing almost an amp. And then, and you could see excess power, let's see, 165 milliamps on standby, which is not good. So we had to be able to completely turn off the module using it, which we had circuitry that would literally cut off the entire module. And you could see it would go down to below below 25 milliamps and into the microamp range if you turned it completely off. But we had to add additional circuit. Today, you don't have to add additional circuit. You just have to use just be able to program the chip to go down into off mode, sleep mode, we call it. I talked a little bit about narrowband 3GPP. This is all supposed to be rolled out in this country, but it's not. Narrowband IoT. I did some initial tests with T-Mobile's permission, written permission, and special SIMs. But then they decided they wanted to stick with LTE-M in this country. I think because they could charge more, probably. That's okay. So here's the advantage of, and it's not just NB-IoT. So LoRa has the same kind of advantages. Low power solution, and NB-IoT enables a portable solution with a 10-year battery life and no vehicle wiring. Well, let me just talk about that for a minute, because when we looked at this closely, I was able to see a powered unit that would operate 2, 3, 4 times a day on the latest, third generation parts like NB-IoT or LTE-Ms that would work on energy harvesting. So so once you reach a point where you can use a tiny solar panel that's less than 3 centimeters, you can power it even in indoor lighting situations. And then you can not use a battery at all, but you can use a super cap that's being charged by a tiny solar cell or motion. I have another design on here that's powered by motion. So you have the potential now of building systems inside of concrete and doing all kinds of things, managing buildings, smart cities, and working fine through concrete. Now, it won't give you 20 kilometers. May not give you 1 kilometer. We measured over 500 kilometers repeatedly. I have a test data on that. It certainly supports hitting a base station. LoRa requires a gateway. It has not been rolled in certain cities. Like if you live in downtown Philly, they do have gateways that are managed that you can pay for support. But out here, I mean, most of the country is not covered by gateways with LoRa. Now, on the other hand, cellular, it's built in because it's built into the LTE base stations and 5G base stations. Lowest cost solution. The one thing that was cool, and probably the reason why they pulled it from the rollout, the NB-IoT, was they had costed the $6 to $10 a year. So it equals a typical 1 month LTE cost of $6 to $10, but it's a yearly fee. So which is what you need if you want millions and millions of sensor platforms, and of course coverage is, when we talk about 20 kilometers or even 1 kilometer, that's Bluetooth. Bluetooth is range is roughly less than 10 meters. Wi-Fi is good up to about 100 meters. Okay. It just shows you comparison. Now, they're measured in terms of release. So 3GPP has different release numbers. So the parts I have are release 14. And each release, they go lower and lower in power. And they have cycles in the actual handshake with the base station. They can shut down parts of the cycle. They call it extended delay, EDX. All right, so each release is lower power. It's pretty cool. So LTE seems to be the favorite of anybody that wants to go into production. LTE-M, it gives you a 10 dB improvement as opposed to a 20 dB sensitivity improvement with NB-IoT, but it's fully supported if you're roaming at very high speed, the handoff occurs. With NB-IoT, it has to re-register every time. Now I've tested it at 60 and 70 miles an hour going by a base station. you don't notice it unless you're doing something with video. All right, this gives you some idea of the size. So now this is a complete system from Nordic that includes sensors, motion sensor. There's a couple different sensors, 3 different sensors on this board itself. And of course, temperature, accelerometer, and it's got, I believe, barometric pressure. Anyhow, so that's on this tiny Nordic system. They've got the size down lower than this, and they were able to, believe it or not, it's a big deal, I guess, to track reindeer in Iceland. And one of their promotional literature I got was how they track reindeer with NB-IoT. So this is one of their systems I have. Some measurements we took of the differences. Now here was an interesting experiment we did. So we said, my cell phone is a LTE and 5G T-Mobile. So I basically took my development board, LoRa development board, or no, NB-IoT in this case, my NB-IoT board, and I actually calibrated it with a second floor, in a second floor building. There's commands to look at signal strength, and there's all kinds of diagnostic commands on this, which is system commands, which is useful. And then I took it down to a concrete basement, and I actually tucked the antenna inside of concrete. Now, when I even got into this area, my cell phone stopped working. And then I looked at the measurement. I have a measurement tool that's built in that actually looks at the level. And so what I was able to do was measuring the NB-IoT working at -124 and my phone not working at all. So basically where the difference was 17 dB advantage. So in other words, it worked right through the concrete, no problem. This was a test I had done early on. And then we ran further tests in Tom's lab at TCNJ, which is pretty cool. So we have a whole series of tests. They poured concrete cylinders. So we've got various thickness. So we ran a battery. I have this data available, and let's look at it all. It's pretty cool stuff. And couple notable things here, and I colored it in red. One of the things that you look for in hardware, if you want to keep it to a minimum amount of ultra low energy, is you make sure that all the integrated circuit and all the chips are at 1.8 volt, because power is wasted. I mean, it's a higher consumption if you go up to 3 volt, 3.3 volt logic, 3 volt. And it's certainly the old logic is 5 volts, which is even more wasted power. But in this particular case, they actually used a vibration generator that would work on a motor. So this was attached to a motor, and every time the motor was vibrating, it would be generating power to power the sensor platform and transmit energy as narrowband NB-IoT. Okay, let's see. It's about open for any questions anybody has. There's a lot of material I can absorb, but bottom line is we're looking at a lot of bridge and buildings that can be easily retrofit or designed actually when building pouring concrete. If we can get, we're pretty close to having a platform where we can actually put right into the concrete when they're building new homes and new buildings, apartment buildings, where we could look at the modal resonant frequency and look at it as a pattern that changes over time, and look for faults in the structure through MEMS accelerometers. And there's a couple papers that I've been studying that looks like they built it and it's viable. It's funded out of Italian government, but it looks like we're awfully close to doing things like this with bridges and buildings, of looking at the resonant mode under vibration, and you end up I've looked at some of the results. They could even tell the wind velocity just by analyzing the FFT pattern put out by a accelerometer. Okay, guys, any questions at all? Let me go into.
Well, I don't have a question. I just was very interested in this. I entered your Zoom room because I thought this was going to be about health, but I still was fascinated with it. It just tells me about how we're going to be able to monitor bridges better. Now, hopefully we pay attention to those monitors and do the right things to keep the bridges up. My grandfather was a civil engineer. In one of his notebooks, I saw a picture of a collapsed bridge with a dinky locomotive having fallen into a ditch. And obviously that was not something they wanted.
Oh, geez. Well, you say health now. I have a whole series of IEEE papers and Elsevier papers that would take that same architecture I have and map it into a human tracking and human health system. And there's a paper that does an excellent job. If you're interested in that, you know, I could share that. I could post it somewhere. I don't know if we have a system. If Lou's got a system, I can post the paper. But there is an IEEE paper. It just came out 2022 on a much superior, because they use Bluetooth all the time for looking at, you know, various physiological symptoms and so forth. They use Bluetooth to monitor heart rate, blood oxygen level, oxygenation. And now if you replace Bluetooth that goes 10 meters with something that'll go over a kilometer, that's pretty cool. You know, you could almost go directly to your doctor or gateway it up through with a cellular system, and it can call your doctor directly. So there's a lot of need for this, of mapping it over to the sensor platforms are almost identical, whether you go into structure health or human health. You know, size is still important, small as possible. Energy, as low as energy as possible. But people doing energy harvesting off the human body, so there's no batteries required to monitor personal health. So it's a great area for research. It's fantastic. Any other questions? I usually like to have people ask questions during it when it's in the fresh in their mind, you know. The other point that where I didn't stress is that it's not only applicable in human health, but all of a sudden, if I look at peer-reviewed research in IEEE, the number of sensors in the agricultural field, again, it looks identical. It's how do we get the energy out of it? How do we create energy harvesting where we can power it remotely in orchards where we don't have to go out and change batteries? So it's a huge deal. With a new paper just came out on identifying worms in apple orchards. So you got a huge apple orchards. Apparently there's one very dangerous pest that can wipe out your apple orchard. So they've got a small camera, and then they do a machine learning map, and then they send it through LPWAN technology out to a central gateway, a huge orchard. I thought that was pretty cool. There's a paper on that that's very interesting. So the applications in structural health, human health, and then agricultural. Precision agriculture, they call it. But it's, you look at the architecture, it's the same thing. The same thing I drew before. It's on the same research papers. Okay, that's about it, guys. If you don't have any questions, I'm good.
Well, thank you so much, Professor Jessen, for an amazing talk. I think next up we have the keynote speaker at 3:40 p.m. in track 1. If everyone wants to take like a little bit break. and then reconvene. But once again, thank you so much. This was, I personally have learned a lot.
Oh, thanks.
Yeah.
Very good. Take care.